Welcome to the Optical Modulation Analyzer introductory video, brought to you by Coherent Solutions in partnership with Teledyne LeCroy. In this video, we'll give an overview of the Optical Modulation Analyzer, or OMA for short. We'll touch on the powerful analysis capability of the Optical Link software and show its remarkable ease of use. Let's begin by examining the hardware configuration. The Optical Modulation Analyzer is shown in front of you here. We start by inserting the signal under test into the coherent receiver, which is shown here. The purpose of the coherent receiver is to convert the complex modulation format, which is an optical signal, into its 4 electrical tributaries. These 4 analog signals are then passed to the acquisition unit, which is shown here. The acquisition unit converts the analog signal into the digital waveforms. Those digital signals are passed from the acquisition unit to the MCM. The MCM is a powerful processor. It contains the MAUI application which controls the entire OMA system. The MAUI software has an analysis package called the Optical Link. So all of the DSP, visualizations, and performance metrics are shown here in the MCM. Having the Optical Modulation Analyzer configured in this fashion gives you a lot of flexibility. For example, you could replace this golden coherent receiver with your own receiver and test its performance in your system. You still get to use all the powerful analysis capability in the Optical Link OMA software using your own receiver. Or, in the future, you could upgrade this acquisition unit to a higher bandwidth acquisition unit. So what's the purpose of an optical modulation analyzer? Well, there are 2 main applications. The first is to fully characterize your optical signal. So that's providing you information on the optical amplitude, phase, and the state of polarization for your signal. In this case, the Optical Modulation Analyzer is set up to manipulate your signal as little as possible in order to give you the most accurate representation of your optical electric field. This is the default configuration of the Optical Link software. A second application is to mimic commercial coherent receivers. In this application, you may want to decrease the receiver bandwidth, use match filter designs to match the filter in the transmitter, use DSP algorithms with equalizers to increase the eye opening and give you the best bit error rate performance possible. Both of these applications are possible with the Optical Link and OMA system. So let's explore the OMA in more detail. You can access the OMA software by clicking on Analysis, followed by the OMA icon. This brings up the OMA panel on the bottom of your display. Click on Enable OMA. This will reconfigure the display in the OMA style. Now, to start your analysis, you only need to provide 3 basic pieces of information about your signal. By going to the right-hand side, you can specify whether it's single pole or dual polarization signal, the modulation format. In this case, we'll start with a 16 QAM example. Specify the symbol rate. For this example, it'll be 32 Gbaud. So now that we've defined those 3 basic pieces of information, you can click Run or Single. Now the OMA software will then start to gather the signals, configure the scales of the oscilloscope automatically in order to give you the best possible performance. All you need to do is let the OMA software perform its calibration. So now that the calibration is complete, The OMA has fully characterized the electric field, so the amplitude, the phase, and the polarization of your signal are completely characterized. The OMA software can show you this information in many different ways. This information is all represented under the Graphs section. So the traces show you all the signals versus time. So you can look at the in-phase and quadrature components versus time. You can look at the intensity, or the phase, or the error vector magnitude versus time, as well as the phase error for the EVM and the carrier phase. You can also look at state of polarization, the 3 Stokes parameters versus time, as well as look at the raw signals that have been captured before any digital signal processing. The fourth tab is the spectrum. So you can look at the spectrum of the electric field, or the spectrum of any of the individual in-phase and quadrature components. So we can zoom into our spectrum and look at that spectrum in more detail. Under the IQ category of graphs are all the signals that are shown on this IQ plot. So you can see the trajectories, which is basically the path taken to get between symbols. The constellation points, which are the symbols which are carrying the binary data, as well as the reference symbols, which are shown as green crosses, show you the ideal location for the symbols. Under the I plots are the signals shown over 2 symbol periods. So in this case, we're showing the in-phase and quadrature I diagrams, so we can see those located here. But you could also see the intensity and phase over 2 symbol periods. So here we see the multiple phase levels associated with this 16 QAM constellation. You can also look at the error vector magnitude over 2 symbol periods. So this shows us that our error vector magnitude is at a minimum when we're at our symbol period, and as we start to deviate away from that symbol period, our error vector magnitude goes up as we're transitioning between symbols. And then it goes back down again as we start to get closer to the symbol. So we get this bowl type function for the error vector magnitude shown over 2 symbol periods. You can also enable all your parametric measurements by going to the measurements section and clicking on parameters. On the right hand side, you see 2 tabs with all of the performance metrics available for your modulation format. So we see things like the error vector magnitude, which is an RMS number, and all of the performance metrics show up immediately below your graphing windows. You can also show the EVM as a Q factor or bit error rate estimate. The bit error rate estimate gives you a quick and easy way to estimate the bit error ratio of the signal under test. You can also examine the bias errors on your signal, the quadrature errors. Also shown are things like the skew between the in-phase and quadrature components, the IQ offset, which is another way of showing the bias errors, the IQ imbalance. The imbalance is really the RF imbalance between the in-phase and quadrature components. Here we're showing the frequency offset between the laser from the signal under test and the local oscillator from the coherent receiver. In this case, we see that it has a frequency offset of about 412 megahertz. You can also see the magnitude and the phase error components of the error vector magnitude. To get the performance metrics related to polarization, you can click on the Measure Pol Demux tab. This will show you things like polarization mode dispersion, the skew between the X and Y pole signals, as well as the polarization dependent loss. In this particular case, the signal is back-to-back, so the PMD and PDL are extremely low. So under the measurements section, you'll find the BER button. By enabling this functionality, you're accessing the true bit error ratio counting capability within the optical link. So this converts the detected modulation format into the various binary streams contained within your modulation format. So the BER will compare that binary data to the known binary sequence that you've transmitted. It'll then count errors and accumulate those errors over time, giving you an accurate representation of the system performance. So let's see how this is done. Click on BER, you can then enable BER. Now there are many different ways in which your data can be multiplexed onto the signal under test. 3 basic ways are shown here as independent, multiplexed IQ, and multiplexed XY. Independent reflects the fact that the in-phase and quadrature components have completely independent PRBS data or your own custom data. Multiplexed IQ means that a particular PRBS pattern is then multiplexed out to the in-phase and quadrature components. And multiplexed XY says that the particular PRBS pattern is then multiplexed out to the X pole and Y pole, and then that data is again multiplexed out to the in-phase and quadrature components. In this particular example, we have a PRBS pattern that's being applied to X pole and a different PRBS pattern that's applied to Y pole. So we're selecting multiplexed IQ. There are different encoding styles that can be chosen. So you have binary encoding or various gray codes. These options are shown dependent on the modulation format that you've selected. You can also choose custom and change the encoding style by clicking on View and Edit. So this gives you a template to start from. This is the default encoding for these selections of symbols. This is the binary representation, and these are the symbols, real and imaginary locations. So you can modify any of these binary codes. So in our example, we've got a binary encoding. Under the Pattern tab, you can select the pattern that's being applied to the signal under test. So you can select the data applied by clicking on the Pattern button. So here there's a default selection of PRBS patterns, anything from 2 to the 3 minus 1 up to 2 to the 31 minus 1. And of course, you can add your own binary sequence by clicking on Custom and specifying the binary sequence. So in our example, we're applying a pattern of 2 to the 31 minus 1 on X pole and a pattern of 2 to the 15 minus 1 on Y pole. So now we're ready to go look at our results. So we'll click on the Bit Error Rate tab, and here we see the results. So we can see the results broken up by X pole and Y pole. The checkbox shows that both of these signals are locked, so they've identified the PRBS pattern that you've specified, and now they're starting to count errors. So the bit error ratio here is 0, since it's found 0 errors. Of course, you can see that we have a nice signal to noise ratio, and so you would expect to be error-free in this case. So this is broken up by X and Y pole and showing you the aggregate bit error rate for the total signal. If our signals were accumulating, this total number of bits would accumulate, as would the error count, and this would be reflected in the bit error ratio. Okay, so let's look at how we can control the digital signal processing functionality within the OMA software. Start by clicking on Digital Signal Processing. This brings up the DSP window on the right-hand side. There are 3 main paths for the DSP: dispersion compensation, polarization demultiplexing, and then carrier recovery, which consists of carrier offset as well as carrier phase recovery. Under dispersion compensation, you can choose between frequency domain algorithms, time domain. By choosing custom algorithm, it will open a MATLAB window and let you directly enter your own MATLAB algorithms. We'll look at this in more detail shortly. Or you can bypass dispersion compensation altogether by clicking on None. In this case, since we're back-to-back, we're going to select None. For polarization demultiplexing, we have a number of built-in algorithms. The constant modulus algorithm, which is suitable for phase-modulated signals like BPSK, QPSK, APSK, or the multimodulus algorithm, which is what we've selected now, which is suitable for signals like this 16 QAM or 64 QAM. Again, you can choose custom and enter in your own MATLAB code, or choose none. If we were in single polarization mode, the option to use this max ratio algorithm would be enabled. In carrier recovery, there's a Viterbi algorithm or the decision-directed algorithm, which is what we've selected here, which is more suitable for QAM-type signals. Again, you can choose custom and insert your own MATLAB code, or select none to bypass this algorithm entirely. Let's have a look at how you'd enter in your own MATLAB code. You can click on Custom, and this will start the MATLAB runtime engine. By clicking on the Demux Custom tab, you can go and specify the location of your MATLAB code. So let's click Edit Code and Load from File. By default, we provide you 3 example files for you to start from so that you can enter in your own MATLAB code and modify these files. This lets you get started quickly and efficiently. So we've got a pole Demux example. So let's go ahead and load that. So here you see the MATLAB code. So this is an example of the constant modulus algorithm. So we close the window, and your MATLAB code is inserted directly into the DSP process. So now we see the result of your MATLAB polarization demultiplexing. So now let's switch back to one of our built-in algorithms. So we'll switch back to MMA. By clicking on the Demux MMA tab, you can now configure the parameters of the MMA algorithm. So in these parameters, you see the gradient, which controls the speed at which the algorithm will converge, the number of symbols that we're using to converge over, as well as the number of taps in an equalizer. In this case, we've got a single tap, so there is effectively no equalizer. So we can turn this up and say enter 17 taps, effectively enabling an FIR equalizer within the MMA algorithm. So you'll notice that our EVMs will then improve. So we've got improvements down to about 6% in our EVM. These symbols have then tightened up, and the openings of our eyes have improved. So we've basically corrected for lower frequency response of the transmitter by introducing an FIR equalizer. So you can also access any of the parameters for any of the other built-in algorithms by simply clicking on their corresponding DSP tabs. Now let's examine some more advanced functionality that's possible with the Optical Link software. Since the Optical Link is fully integrated into the MAUI application, we can pass all the signals that are acquired and measured within the Optical Link to the MAUI application. So this lets us perform math functionalities, measurements, acquire statistics, pass data into MATLAB, or even perform, say, clock recovery within another analysis package called the Serial Data Analysis package in the Optical Link. So everything is possible once the data is passed from Optical Link to the MAUI application. So let's see how this is done. If you click on Measure and Measure Setup, in the bottom window, you'll see all the various measurements which are available to you. So let's go ahead and configure, say, measurement number 4. We'll turn that on, and we'll click on Source. These are all the signal sources that are available to you. You'll notice that there's an OMA button. If you click on OMA, these are all the OMA signals that are present. You can perform measurements on any of these available signals. So let's use, say, the 3 Stoke parameters that define polarization versus time. So let's select S1 and perform a measurement. So I click on Measure. These are all the various parameters or categories of measurements that are available to me. So let's measure the mean value of S1. So I can click on vertical and mean. So now I'll be performing the mean measurement on this Stokes vector. So let's go ahead and show the table. So this is the measurement that we just configured, P4, and we're showing the mean value of the S1 component of the Stokes vector. So using this functionality, you can perform measurements on any of the signals, traces, eye diagrams available within the OMA. You can also perform statistics on the performance metrics. So here's an example where we're performing statistics on the EVM of XPO by using the math operator called identity. This will then show statistics, and these values will accumulate over time. There are an unlimited number of measurements that can be performed on both the parameters and any of the signals, whether they are time domain or frequency domain. So that's just one example of the more advanced features that's possible with the optical link and the optical modulation analyzer system. So it really is that simple and that powerful. All of your controls are at your fingertips, and the optical modulation analyzer system is flexible and fully configurable. So thank you from Coherent Solutions and Teledyne LeCroy. Please contact us to arrange your demo.